And today we will talk about how we use Cassandra here at Ooyala. What problem are we trying to solve by using Cassandra and Cassandra and Spark? And we'll discuss our Spark and Cassandra architecture. Oh, and a little demo. By the way, I presented this talk at the Cassandra Summit, and that's available online as well if you're interested in the slides. I have a few updates here, but it's mostly the same. So who are we? Our motto is we power personalized video experiences across all screens. If you watch a video on ESPN.com, Victoria's Secret, REI, you've probably used our technology without realizing it. We founded about 6 years ago, and ever since the beginning, analytics has been like pretty important to our strategy. We get it's well over 2 billion events a day from people watching all kinds of videos on customer websites. So yeah, some of our customers. We're a fairly large Cassandra user. We have 12 clusters, from 3 nodes to 107 nodes. About, I don't know, 28 terabytes managed. Easily over 2 billion Cassandra column writes per day. It powers like most of our analytics infrastructure from the standard slice and dice aggregates that customers use to discovery, recommendations, trend analysis. We run a range of Cassandra versions from 1.0 to 1.2. And our largest cluster is one of the biggest Cassandra installations around. So, yeah. What problem are we trying to solve? Where we're trying to go is, so we have mountains of raw data. So much like it just overwhelms you don't really know what to do with it. We kind of want to get to, a few nuggets, a few gems, right? And we want to do this quickly, painlessly, and at scale, right? I guess that's sort of the answer to everyone's trying to solve, right? What we have today is that we have pre-computed aggregates. We have video metrics. They're computed along several dimensions, such as geography, country, city, device type, browser, platform. There are a few other things like that. So this is fine. So if basically I want to look up, say I am ESPN, and I want to look up what are my top videos in the US, or what are my top videos by device type, whether it's mobile or a tablet, whatever. That's very easy. We just pull out a key from Cassandra. It's pre-computed. So this is nice. It's very fast. The downside is that it's very inflexible, and it's very difficult to change. And most of the aggregates and indexes are in fact not read. For example, we store a sorted list of, say, videos by city. Most people are only interested in the top few cities. Very few people are interested in the tail end of things, right? And what if we need more dynamic queries? Like, I want to mix several dimensions together. Top content for mobile users in France. I want to do data mining. I want to do a bit more interesting stuff. When I start to move to the more advanced use cases, then, excuse me for a minute. Okay, sorry, just have to wait 1 minute. Eventually you'll find it. So, there we go. Okay, so in the more advanced use cases, then this model starts to break down of just pre-computing these aggregates. For example, let's say you have 100,000 cities, and let's say that you have 1,000 browser combinations. Just doing cross product of 2 dimensions alone will get you like, a huge, I mean, something that's like way too big, right? So basically, imagine that there's a continuum, a scale between static, between pre-computation and dynamic queries, right? So you can think of it as, on one end, you can pre-compute everything, and that's what your customers will look up. So this is nice, but it's inflexible. On the other hand, you can do dynamic queries over your data. This might be like, slow. This is very flexible, but might be very slow. And what we really want is to kind of like have a medium where you can pre-compute your common queries. You can have flexible and fast dynamic queries, and easily generate a lot of materialized views to suit your different needs, right? So that's what you really want, is something, kind of a medium. Now, if we look at some industry trends, you have some new technologies coming out for fast query execution. Cloudera Impala Drill is a new coming project. You probably all heard about Presto. You have in-memory databases. You have a lot of streaming and real-time frameworks that are coming out. And even for traditional Hadoop, you have things like cascading and Pig that allow you to write queries faster, right? So maybe, we can see if a combination of these technologies, or something, can help us solve our pressing data problem, right? So I'm going to talk about why we believe Spark and Shark is the answer for our problem. So just a quick introduction for those of you guys that haven't heard of Spark. It is an in-memory distributed computing framework. That doesn't mean that all the data has to be in memory. It does have modes for spilling the disk and keeping data on disk. It was created by the UC Berkeley AMP Lab 3 years ago. And it initially targeted problems that MR is traditionally bad at, namely iterative algorithms, interactive data mining. And since then, people have started using it for a lot of general use cases. We just came from the, just this week, there was a Spark Summit, and the first ever Spark Summit, and it's pretty incredible. The number of applications that people are doing with Spark is really, really incredible. There are active contributions from at least 15 companies. This is like in June, so the number has probably increased. So let's recap what the Hadoop paradigm is. So you have a distributed file system, XGFS, or any number of replacement DFSs. And when you do a map reduce phase, XGFS, you read data from XGFS, and then you, after you shuffle the data, you do a reduce, you write the data back to XGFS. Then you read it again. Now, for simple jobs, this might be okay. Like the more complex your job is, the more stages you have, and so you find that you're reading and writing from XGFS a lot, and that quickly starts to dominate your I/O. The Spark paradigm is, let's say that I have 2 data sources, and the first thing you notice is that you're not limited to just map and reduce. You have some higher level operators, such as join. So I can take the data sets, transform one, join them together, and then this is where the magic happens. I can cache a resulting data set in memory. From this point onward, I can then do transformations on the cache data set very quickly because it's all in memory. What we found is that in terms of throughput, memory really is king. So we did this experiment in the first case, reading from Cassandra with the cache being code, just from a location you haven't read in for a long time. If you are able to warm the cache effectively, this is a dramatic increase, like maybe 8x to 10x at least. So using your cache effectively helps you a lot. Cassandra also has a lot of caching options. As you guys probably know, there's row cache and different kinds of things. But if I was to put this data in Spark in an in-memory data set, that is another 1 to 2 orders of magnitude faster. We found that developers really like Spark. One of our engineers looked at it for 30 minutes, was able to get up and running and write jobs right away. The collections API is very high level, so it allows you to think in terms of high-level transformations. And you have three languages for you to implement Spark jobs. You have an interactive shell, which allows for, you can basically play with your data and just type, let me map my data and transform it in a certain way and kind of get results out, pretty quickly for testing. And the low latency, you lead to quick development cycles. And these days, oftentimes the only advantage that a lot of startups have or companies have is basically developer velocity. So that's something that we find very important. So on the right is our Hadoop word count example. I had to shrink it to a 4-point font just to get it to fit. On the left is our Spark word count example. It's just 4 lines. I'll touch on the Spark ecosystem a little bit. So what do we have here? So Spark is not just a Hadoop replacement. It has a bunch of other projects that build on top of it. One is an underlying layer. There's a project called Tachyon, which is like an in-memory caching for HDFS that allows very fast reads. There is a project called Bagel, which is Google Prego, the graph algorithm on Spark. You guys might have heard of Shark. This is basically Hive on Spark. Finally, there's Spark Streaming, which is, you can think of it as micro batches. So the batches can be as small as a second or half a second, and that way you can get real-time computation, fault tolerant. Wait a minute, sorry. So Shark is 100% Hive QL compatible because it actually embeds Hive, but it is much faster. However, it can actually reuse all of your Hive storage handlers, SerDes, and other things like that. I'll touch on this in a minute. If you're running DSE, you can still use DSE and Cassandra FS for your Hive metastore. One thing is that Shark has integration with Spark, so you can, for the things that SQL is not good at expressing, what you can do is you can have a query in HiveQL and then use Scala and Java code to transform your data in a way that is not possible with HiveQL. So that's just an alternative to writing UDFs. We'll talk about our new architecture a little bit and how we integrate Cassandra and Spark and Shark. So on the left are what we call raw events. Basically, every time you watch a video on one of our customers' websites like ESPN, you have a little bit JavaScript module or ActionScript module, which is sending data even when the video displays and when you play or you skip forward. So it's sending events to our servers. So that's what I mean by raw events. From here, we have an ingestion pipeline that will write it to Cassandra and what we call an event store. From here, we then use Spark to create various materialized views. And the way that we then utilize these materialized views is that we can use Spark to do quick predefined queries, or maybe we can run ad hoc HiveQL queries in Shark. Both are available. a little bit about how we actually physically organize our clusters. We'll start with Cassandra on the nodes. On top of Cassandra, we put an input format and SERDI. I'll go into detail about why we have. We basically wrote our own input format, and I'll go into detail in just a second about why we did that. And sitting on top of the input format is a Spark worker that will pull the events from Cassandra. If you want to use like Shark or Hive, then you can, on top of the input format, there's something called a SERDI, which basically translates raw events into the columns of a Hive or Shark table. Coordinating all of the Spark workers is a Spark master. And then we also have a REST Spark job server that we actually just open sourced that makes it easy for you to run jobs on Spark. So our schema is kind of a, it's a variation on a standard time series. Basically, you have an ID or a user, and you have events at various times. We use the time as the column key in facts. However, we actually have a separate column family called an attribute column family. The reason why we do this is because there are a lot of attributes, such as a user's IP address, user agent, things like that, which repeat again and again. So we keep them in a separate column family to, one, it saves a huge amount of space and I/O, and two, it allows us to easily generate indexes and to annotate attributes after the fact if we want to. And so the way that we unpack, you can think of the job as like, in Cassandra you have rows and columns in a time series. And now what we want to do is we want to extract you can think of them as JSON blobs, and expand this into an SQL-like table for data warehousing. So you can think of each cell maps to one row. This is actually very similar to how Cql reads out data. So your user ID, which is essentially part of the row key, gets one column. Then the different fields in the JSON would get mapped out into their own columns. And so we just go from left to right, and then down to subsequent rows, and that way, this returns the data in a format that you can easily run, for example, a Shark queries against. All right, this slide is, by the way, not in the Cassandra Summit presentation. Different options for integrating Spark with Cassandra. First is that you can use a Hadoop input format. Spark will use any existing Hadoop input format out of the box. So the choices are, you have built into Cassandra a column family input format. This was really the only option, built-in option before, I think 1.2, I'm not quite sure. This read all the rows from one column family. In more recent versions, there is now something called a Cql Paging input format, which is pretty nice. You can actually give it a Cql query, and it will read out the relevant data for you. And it pages so that it will also handle wide rows pretty well, as well as it supports secondary indexes. Now, you can also roll your own. I'll just back up to say Hadoop input format, let me see. So at the time that we did this integration, we hadn't looked into Cassandra 1.2 yet. So we didn't look at the Cql Paging input format. So, and the other thing is that because of our layout, we have like multiple column families and our own indexes. We just wrote our own input format. Now, you can also read data from any source in Spark without an input format. The big disadvantage is that without an input format, you can't write standard Hadoop jobs, like standard MR jobs. However, it's actually much easier to develop, to read from Cassandra without an input format. You can essentially do it in one line. that line right here that says sc.parallelize, what I'm doing is Spark has a parallelize operator that will take any list. Let's say I have a list of row keys, 1,000 row keys, and I want to read these rows from Cassandra into Spark. What parallelize does is it takes that 1,000 list element and distributes it across the cluster. Then what the flat map does is it takes each row key, and then you can have something that reads all the columns from that row key. And so you end up in one line with something that can, in a distributed manner, read a whole bunch of rows from Cassandra. So if you don't care about Hadoop compatibility, or rather MapReduce compatibility, you can actually save yourselves probably like, I don't know, 2 weeks to a month or whatever, developing the input format. There's also a JDBC RDD, so RDD is a Spark term that stands for Resilient Distributed Dataset. This is sort of like the base abstraction in Spark, and it's basically a dataset that is stored in memory and can be transformed. You can also use the Cassandra JDBC driver with the JDBC support and do things that way. So there's actually a fair number of options. Lastly, there are companies that are starting to open source some Spark and Cassandra integration. So I just have one link there that you might want to check out. If you do develop your own input format, just a couple of tips to throw out. You want to know which target platforms you're developing for. If you've done Hadoop input format development, you would, or you just know about input formats, you know that there are 2 Hadoop APIs. There's a new API and an old API. Plan this carefully because they are incompatible but similar enough to be very confusing. And some things that build on top of it, for example, cascading. I'm not sure if it's, so cascading will, for example, only work, Hive up to, until very recent versions, will only work with the old Hadoop API. You need to be prepared to spend time tuning your split computation. So I'll give you an example. If you have your own indexes in Cassandra, that could be a very long row. You don't want to spend a lot of time reading that one row out in your input format, because input format has to do, when you're computing splits, that's all done on one node, and it's not distributed. You might want to consider sorting row keys by Cassandra token for data locality. And if you're using Hive, you can implement predicate pushdown in your Hive storage handler, which will let, for example, I have a where clause. You can have an input format only read from rows that contain the data you're interested in. Just a quick example of how we use it for OLAP processing. So out of the raw events, we use Spark to create OLAP aggregates. And then we combine them and run queries against it, different kinds of queries. Let's see, in terms of performance numbers. So this is sort of like the earlier graph I showed you. For reading from Cassandra with a code cache, takes, I don't know, maybe 2 minutes to read, 1.5 million events. Oops, wait a minute. When we read it again and again, the cache warms up, and this drops by a factor of 3 or 4. When we process the data in memory, then we can get that out in like well under a second. So here's how we actually, here's the workflow for Spark and how we do our processing. First, we start an aggregation job in Spark through our job server. This basically will read data from Cassandra, the raw events, and process them and create some aggregates. The aggregates are stored as a data set in memory, distributed amongst all the different Spark worker nodes. Then what we can do is that we can run a query job that taps into this data set and return results. and you kind of do this again and again, which keeps the aggregated data warm in memory and allows you to run fast queries. A quick note about fault tolerance. The cache data set lives in a Java heap only. What happens if the process dies? So Spark has something called Lineage, which is that it remembers for every computation how the computation, the exact transformations that you ran. So it's designed to, in the case of failure, go back and rerun your source computation so that you can end up with the same aggregates. Now, obviously, this is rather expensive. You need to, in the case of Cassandra, you need to read from Cassandra again and do the aggregates, which might not be what you want. It turns out you can also replicate a cache data set. So you can replicate on another node to survive single node failures. That's another strategy. What we do is we simply persist our aggregates or materialized views back into Cassandra, and then we just load it into cache. This also enables us to have multiple sets of Spark worker nodes that process this data for high availability and other reasons. So we like this approach. It also allows us to easily inspect our materialized views in Cassandra. Let me see. There's another option now that Spark's project Tachyon will allow you to cache. Basically, it allows you to use it as a write-through cache to HDFS. And if you use HDFS, or you can use Cassandra FS, for example, then it will cache the data in memory so that you don't have to read it back again. Essentially, the data is stored already in memory. Question? Okay, I'll take this. So about Storm versus Spark. So I would say Storm and Spark are kind of like designed to address very different problems. Storm is for streaming, and you want to stream from a never-ending data source. Storm is very good for that. I guess we look at this a little differently, in that we are reading chunks of data. So we think of this as more like Spark. If you use Spark itself, we still have Storm systems in production. So this doesn't replace Storm. I would say that if you want to use something like Spark streaming, that might replace Storm. But I would say this use of Spark is more like replaces Hadoop for enabling extremely fast batch jobs. Sure. Why don't we take this? Why don't we take this offline so we can continue? Yeah. Thanks. So I just want to show you guys a quick demo of like Spark and Shark, or rather Shark in progress. This will be a part of this, you watching a video of me typing slowly. So this is a local Shark node with just, one node, creating a table from Cassandra using our input format, creating a cached Shark table in memory, and running fast queries. So the first one is that we do a create external table, and we use our own storage handler, and we use table properties to set which Cassandra node to connect to, what are the start and end times, this kind of thing. And then our input format understands based on these parameters, it can translate that into row keys and column families, et cetera, et cetera. Once you have created that table, that actually doesn't read the data right away. That's just a mapping. Now when I do create table events cached, that actually caches those events in memory as a cache table, and that actually is what reads data from Cassandra. And now we want to query the cache table. For example, I just want to, let's start with the really simple. I'm just going to select count 1 from the cache table. 1.4 million rows. That is relatively fast, half a second. But but the real power comes when, let's do something a little bit more complicated. So I'm going to try to get a count of our various, providers of videos, and you get like this long list. Again, it's extremely fast. This is an extremely fast group by operation. But let's say that what we really want to do is we want to get a top K or top 10 list of videos by count, and so we're going to group. We're going to order by the count, descending, limit 20. So this again returns like pretty fast. So this allows you to do kind of queries that would be pretty slow if you're done from disk. Yeah, and that's it. Thank you very much. We are hiring. So and I think after this also we will have a raffle. Let me see. Where is? Yeah, thank you very much.